Hello, my name is Michael Piero, and I'm going to be showing you how to do a 2D nozzle, C-D nozzle in ANSYS Fluent, and we're going to do a CFD analysis on it with these specifications given. I'm going to be creating the part in Solidworks because that's the CAD program I prefer to use, and I'm going to import that into Fluent. So let's get started. I'm going to make a new part in Solidworks. And I'm going to be using the metric system. We're going to sketch on the front plane. Just going to start with a rough sketch of how the C-D nozzle is going to look. Dimensions aren't really important right now. Okay, and this shape that I have right here, imagine it's half of the C-D nozzle, and it's going to mirror over this x-axis right here. So before we do that, we're going to put in our parameters. So these have already been calculated. So if you have your own specifications, you can put them to what you have. Here. This is the length of our diverging section. And the angle between the x-axis and this line here for the wall of the nozzle is 15 degrees, which is the optimal length. So and one last dimension. Oh, I am missing the third diameter as well. And this is our C-D nozzle. Our sketch of a C-D nozzle. Okay. Now we can mirror this over the placement line that we put down, just like so. And this is our nozzle. Now I'm going to add some fillets to avoid these sharp corners and kind of give a better flow through the nozzle. Okay, and we're also going to add some fillets right here. Okay, so wow, this is our conical C-D 2D nozzle. So now that we finished the sketch, the most important thing we have to do before we put it into ANSYS is to make it a planar surface. And just click OK. And now we have a 2D surface that can be put into ANSYS. Just, okay. So with ANSYS, you can go ahead and open Workbench. I already created a Bell nozzle here and already did a full analysis on it. And I'm going to show how you can compare two nozzles at once in the results tab. But in order to import this part from Solidworks, you must make sure that you have the Solidworks compatibility turned on in the settings of ANSYS. There's many videos out there how to do that. So we're just going to open Fluent, and we're going to click on geometry and change the analysis type to 2D. And now we're going to import geometry, and you're going to import the cone nozzle that we just made. Okay. And everything will be good when you see this green check mark. So we can go ahead and double click on mesh. And this will allow us to mesh our part and define our boundary conditions. Okay, and here's our nozzle. So we can right click on mesh, and we're going to insert the sizing mesh. It's a very simple one. I only have the student version of ANSYS, so you can't make meshes too accurate, or else the program won't run. So we click on our object, in this case our nozzle, and under geometry we apply. And I like to change my element size to 0.01 because I know that's what works and it's accurate enough. But you can play around with it and get something maybe a little bit more accurate. And you're going to click generate. And this is our mesh. It's not too fine, but it's good enough for this simple project. So now we need to click the edge selector and name our inlet and outlet. So this converging part is our inlet, and with the chamber right here, and the diverging section is the outlet. And you can see our inlet and outlet here. And that's all we need to do in the mesh part. So you go back to Workbench and update the mesh. And close this. And double click on setup. And this is now launching Fluent. I like to turn on double precision and click start. And this is going to load the mesh that we just did into Fluent. So it'll pop up whenever it's ready. If you made your mesh too fine, you'll get an error saying that you need to not make it as fine. So, and this is our nozzle, the inlet and the outlet. And for our flow, we're going to be turning the energy equation on, and it's going to be an inviscid flow. And now we are going to create our fluid. I will just call it project 1. It's just the name of a fluid. You can name it whatever. And I'm going to change it to an ideal gas. And I had to calculate CP, and I was giving molecular weight. This is in kilograms per kilomoles, and the CP value is in joules per kilogram per Kelvin. So just want to make sure you have those units right. And this is all we need to do for fluid. And now we can define our given boundaries. So for the inlet, we were given the chamber pressure and chamber temperature. We weren't given any velocities. So we can actually right click on inlet and to change the type to a pressure inlet. And it was 9.7 MPa. So we're going to put this in the gauge total pressure, and we're going to have to put this into the supersonic / initial gauge pressure. And our total temperature was 3,710 Kelvin. And apply these. And then we're going to assume that the nozzle is at sea level. So our exit pressure will be 1 atmosphere. Okay. Now we can go to monitors and click the residual tab. And we're going to increase the accuracy of these residuals. Okay. And now we can initialize what we just did. My program seems to have frozen. Okay, program's not frozen anymore, so we're going to click the standard initialization, and we're going to compute it from the inlet. This part is extremely important. You can see that our initial values will be exactly what we put them in, and click initialize. It'll take, because we made our residuals so accurate, it's going to take a little bit to initialize the solution. But once we initialize, we can then run the calculation, and that'll be it. Okay, so it is initialized, and now we can go to run calculation. I'm going to do 200 iterations, and program's running a little slow. And then we're going to click calculate. And now that we click calculate, we are going to be sitting until it's done. So I will be back as soon as the calculation is done. Okay, after about 5 minutes, our calculation is complete. So we can just take a look, and let's check out the velocity contour. And this is the velocity contour of our nozzle. It starts out subsonic, gets about Mach 1 at the throat, and then accelerates up to 2.77 kilometers per second. And we can verify that by checking the Mach number. The Mach number is right about 1 at the throat, so looks good. So now let's go ahead and change the name of this back in Workbench to Cone Nozzle. Okay, and now we can compare the results of both of these. So let's go ahead and update the solution. and update the results. Okay, and now we can go to under the Component Systems tab in the toolbox and bring out the results. And we're going to drag the results of the Bell nozzle. Just drag it. Okay, instead of dragging results, we drag solution to the results. My apologies. So we can drag the solution from both of these Fluent, from both of these Fluent results. And now when we double click on the results, it'll show us both. And we can get a good side-by-side comparison of the contours as well as other plots that you want to see. And ANSYS is smart enough to put these nozzles right next to each other. So let's go ahead and put them both right here. This is our Bell nozzle, and this is our cone nozzle. We can synchronize, or yeah, okay. So let's get our first contour. We're going to insert, and we'll go contour. We'll name this the velocity contour. Okay. We want to change the location to symmetry 2 because if we just did the inlet, it would only show right here. The variable is velocity. And you can change the number of contour colors right here. So when you click apply, we'll get these nice views of the velocity contour. And when we change the number of contours, say to 5, it'll decrease the amount of color variations we have. So you could go extremely accurate with, say, 50, and you can see a very nice smooth contour, but we'll keep it at 15. How about that? Okay. So now we can add another contour. Insert contour. We'll call this one the pressure contour. And they will pop up underneath the user locations and plots. So we will again change the location to symmetry 2. And pressure is already selected. And we'll put this to number of contours to 15 and apply. Oh, we have to uncheck velocity. And these are our pressures. Very nice. So another thing we can do is we can take the velocity at the center of the nozzle. This is why when I created the part in SolidWorks that I mirrored it over the x-axis, because when you go to make your lines in ANSYS, it makes it a lot easier. So for example, when we create a line, we'll call it the center line. And we don't have to adjust the x coordinate or the y coordinate at all. We only have to adjust the x. So from 0 to, we'll just say 2 meters. It's important to increase the number of samples here to at least 100, or else you're not going to get a lot of data points. So click apply. and our center line applies to both nozzles. You could just put it on the cone nozzle or the bell nozzle if you wanted to, but we're going to do both. And let's calculate the Mach number at the nozzle. So if you were to do that and you were to go create a plot, you would see that the Mach number variable actually isn't there. So we have to create it ourselves. So we're going to go to insert expression, and we will call this the Mach number expression. And we can type in our Mach number. So the Mach number would be velocity divided by the square root of I think we already have, we will create, we need to create the speed of sound first, or we can just do it here. Okay. Velocity divided by square root 1.2 times our R value is right here, 415.725 times temperature. And so now we should have our Mach number. So now we can insert a variable and call this the Mach number. And this will be equal to the Mach number expression. So now we have our user-defined variable here, Mach number. So we're going to create a chart. We'll call it the Mach number chart. And the title will be Mach number along center line. The location will be the center line. And the x-axis, we will do the distance, and the y-axis, we will have our Mach number here. So we just click apply. And now we have the Mach number along our nozzle. So series 1 will be the cone nozzle, and you can see this, this little imperfection right here, and this is why designers use our our bell nozzle versus a cone nozzle. And that is how you do project 1. Thank you very much.